Okay, so we got a problem here that has several parts to it, and I really like this problem because it really takes you through all of the concepts here for confidence intervals, and so it's a really nice problem. So let's go ahead and look at this. The average number of miles driven for a sample of 90 truckers is 547 miles with a standard deviation of 42 miles. Okay, now using this information here, we're going to answer these questions. First of all, what is the point estimate of the true mean number of miles driven by all truckers? So do you remember that way back at the beginning? We talked about the point estimate. Do you remember what that was? It was X bar. In this case, 547 miles. Okay, so there's no formula or anything. You just have to remember that for the point estimate, you just use X bar. Okay, so that's the answer to part A. Now, part B, it wants you to construct a 99% confidence interval. Okay, so I'm going to have to kind of make this a little tight here. But we should be able to fit it. So the center of the interval is the point estimate, 547. So for the margin of error, a 99% confidence interval here. If you look at this, you go back to this table, 99% is 2.58. So we'd have 2.58 times the standard deviation. So the standard deviation is 42 over the square root of N is 90 truckers in our sample. Okay. So I know that's really small. Maybe I could zoom in on that. Okay. And so I take 2.58 times 42 divided by the square root of 90. Okay, so this is my margin of error. Now I'm going to round to the nearest mile because the mean and standard deviation are to the nearest mile. So I'm going to round to 11. Okay. So, and I know it feels like, oh man, I'm losing some precision here, but that's not, that's really not true when you think about it, okay? Because these are all estimates. You don't want a bunch of precision here. We're already kind of estimating, and our precision is the margin of error, okay, is giving us the precision. So 11 is my my margin of error, so I'm going to take 547 minus 11 and 547 plus 11. Should be able to do this in my head. When we subtract 11, I get 536. When we add 11, I get 558. Okay, so let me move over. So there you go. That's my 99% confidence interval. So part C asked me to interpret the interval. So I would say that I am 99% confident the true mean number of miles driven by all truckers is in the interval. Okay, so I wouldn't say here, I wouldn't say that 99% of all truckers drive within that interval. Okay, you could have a lot of truckers that drive less, maybe local truckers, a lot of truckers that drive more, possibly, but when you average it here, you're 99% confident the true mean is in that interval somewhere. Okay, so now it wants me to construct a 90% confidence interval. Maybe I'll zoom out just a little bit. A 90% confidence interval. So I'm going to do that right here. So the center doesn't change, 547. So my margin of error, 90%. So let's go back to my table here. For 90%, the critical value is 1.65. So 1.65 times the standard deviation was 42 over the square root of 90. Okay, so putting this in my calculator, so I get 1.64 or 65 times 42 divided by the square root of 90. Just like that. And I get, okay, so I'm going to round to the nearest mile again. I get 7. So this is 7 here. So this is 547 minus 7, 547 plus 7. So my interval here would be 540 to 554. Okay? So now, this next question asks which interval is more precise and why? Why is it more precise? So, looking at these two intervals, which one is more precise? Okay, is it the 99% confidence interval or the 90% confidence interval? Okay, the answer is the 90% confidence interval is more precise. Okay, because it narrowed it down. Okay, it shrunk the margin of error. The margin of error went from 11 to 7, and that made your interval narrow, more narrow. Okay, what you can do is you can think of this as I gained precision here, but I traded away confidence. I had 99% confidence, and to get this precision, I had to trade away. Now I'm only 90% confident in this estimate. Okay, so I've traded away precision to gain confidence. So here, the 90% is more precise. Okay, why is that? I traded away precision, or I'm sorry, I traded away confidence to gain precision. I hope I said that correctly above. I could have switched it around. So I'm more precise now, but what did I have to trade away to get this precision down here? I had to trade away some of my confidence, right? So one way you can think of this is it's kind of 6 of one, half a dozen of the other, right? Sure, this is more precise, but I'm just less confident. The only reason it's more precise is because I'm less confident. And here I am more confident in this, but I just widen my interval. So of course, if I widen my interval, I'm going to be a little more confident, right? You're kind of trading one for the other, almost like you're playing a game. What would be nice is if there's another way that you could gain precision and still maintain that high level of confidence. So let's say I want to maintain my 99% confidence. I don't want to trade away any of this confidence. Okay, so here I had 11, right? My margin of error was 11, and by trading away confidence, I got it down to 7. But let's say I want to maintain 99% confidence, and I want my margin of error to only be within 5 miles, even better than this one. Okay? There's a way that I can do that, and if you look at these formulas, you can kind of see how. The way you can do it is you can make your n bigger, because if I divide, when I take by the square root of n, I divide by the square root of n, that's going to shrink this number down. It's going to make my margin of error smaller. Okay? So you can actually gain precision by increasing the sample size. And you can actually do it without trading away any confidence. Okay? So this last question here asks, how large would the sample need to be for the margin of error to be within 5 miles at the 99% confidence level? Okay? And so, let's call this the sample size formula. That's a nice simple name for this. And this formula basically gives you how big your sample would need to be in order to gain a desired level of confidence. And basically, the formula is this. zeta alpha over 2 times the standard deviation over E, that quantity squared. Okay, and this is where E is the desired margin of error. Okay, so let me zoom in on that. So basically, you want a certain confidence level. That's where your zeta alpha over 2 comes from. You got your standard deviation. You divide that by the desired margin of error, and then you square all that, and that actually gives you the sample size. Okay? This isn't very difficult to derive. I'm not going to derive it, but basically, if you took the margin of error and set it equal to E, and then you solve for N, that's where this formula comes from. Okay? But basically, all I want you to do is be able to use this formula. Okay? So let's actually answer the example that we're given here. So basically, I want 99% confidence level. Okay? My sigma is 42. And I want my E to be within 5 miles. So now I can determine my sample size. Okay, for the 99% confidence, the critical Z value is 2.58. Multiply that by 42. Divide all that by 5. Okay, so the desired margin of error on bottom. And then you're going to square that. Okay, and this is going to give you your N. So let's see. 2.58 times 42 divided by 5. Don't square it yet. Make sure you do the calculation in the parentheses. And now I'm going to square the answer. And look, I get this here. It's 469.67 is what that is, and it kind of goes, and then that would round up to 470. Okay, because your sample size has to be a whole number, so you're going to round this to a whole number. And then the book is always going to say, for this one calculation, you're going to always round up to the next whole number. You're never going to round down. Even if you would normally, like if this were 27, you would still round up to 470. And the reason is, if you round down, then your margin of error will be a little more than 5. Okay, but if you round up, it'll be a little less than 5. And so, by always rounding up, you're just ensuring that your precision is going to be a little more precise than what you want it, not a little less precise. So for this, you would always round up. Okay? So, basically, if you think about this, this is really nice. Okay? There's a lot here. But it's really nice because with this formula, basically what you can do is you can decide on your confidence level. Okay, you can get about as precise as you want. You know, in this case, up to 99%. So you can decide on that, and then you can even choose a precision. And your precision is basically the margin of error. And the smaller your margin of error, the more precise. So within reason, you can choose your precision. And then, as long as you're willing to take out a large enough sample, in this case, 470 truckers, okay, that is kind of a large sample. But if you're willing to take it out, you can then calculate an estimate, a confidence interval that has the desired level of confidence and the desired precision. Okay, so that is really nice. One thing to notice here is that you can never get 100% precision, because 100% precision would be a margin of error of 0, and you can't have a 0 in the denominator because you cannot divide by 0. Okay, so you have to have at least a little bit of margin of error in order to do it. Okay, as long as you're willing to pick a large enough sample. And as this thing gets smaller and smaller, this thing starts increasing very rapidly. So it's within reason. You can get a pretty good precision within reason. Okay, but let's say I wanted a mile, my precision to be within a mile. So let's just see how big my sample would have to be. 42, and then I'm going to divide by 1, right? And then I'm going to square that. So you see here the 11,741 truckers, right? So if I wanted it to be within a mile, that's a pretty large sample. I probably could never get it within a mile, okay? But within reason, you can get a very good level of precision, okay? So I'm going to do one more video here. Basically, it's going to be another problem like this one. And I want you to pause it, and I want you to work through the whole problem, because then you get practice on this whole thing, okay? And so why don't you? I'll put it up. You pause the camera, and you work through the whole problem, and then you can start it up again, and then watch and see how you did.